Good morning. Today we're going to get started with acids and bases. So I have the notes posted. There's a set of completed notes, as you can see here. So I'm going to be using this. There's also a Word document with blank spaces that you can type notes in if you'd like. So whichever works best for you, please go right ahead. Today we're just going to talk about the introduction, what is an acid and a base, and we're going to talk about the Arrhenius theory of acids and bases. So this is just the first two pages we're going to start with, and then tomorrow we're going to talk about Bronsted and Lowry theory, which is on the third page, and then we'll do some practice with that tomorrow. All right, so the first thing to talk about with acids and bases are the properties. What is a property of an acid and a base? Now, what's nice is that many of these properties are the same for acids and bases. So at the top here, we have some common acids and bases. Vinegar, lemon juice, basically anything citrus is acidic. And then some common bases, ammonia, egg whites, and soap are actually all bases. Your blood is slightly basic, but there's a lot of things that you have around your house and you use on a daily basis that are either acidic or basic. So when we look at our properties, I want you to take a moment and read through these. Okay, some of these properties are chemical properties, how they react with other substances. Some of them are properties on ways to tell if it's an acid or base, like with the indicators. So with acids, we have sour taste. Now, taste is only if it is something you normally eat. I'm not saying go out and get a beaker of hydrochloric acid and put it back, okay? We're not talking about that. This is where we're talking about those lemons and that vinegar. You know what a sour taste is. Sour Patch Kids, Warheads, any of those candies. If you read the ingredients, you'll notice that there are some acids listed as an ingredient. And those acids are specifically there to give those candies those sour tastes. An electrolyte, okay? Acids are electrolytes, so we're bases. At the bottom, I have the definition. An electrolyte, a liquid or solution that can conduct electricity. So normally when we discuss electrolytes, it's a substance that when you dissolve it in water, you're able to conduct electricity with it. So if you have anything with mobile charges, remember that's our definition for anything that can conduct electricity. It has mobile charges. So when you dissolve a substance into water and it breaks up into positive and negative ions, okay, right there, that will carry the electrical current. And the ability to conduct depends on the concentration. So that means the more ions you got, the better the conductor it's going to be. We'll get back to that a little bit later when we talk about stronger and weaker acids and bases. Acids react with active metals to form hydrogen gas. You may remember early in the year, actually very early in the year, we did a lab where we took some magnesium metal and we put it into hydrochloric acid, and there was a whole lot of bubbling. Those bubbles were the hydrogen gas bubbles escaping from that single replacement reaction. So the magnesium went into solution and the hydrogen gas bubbled out. Acids change color with indicators. Indicators, we will learn, are chemicals that change color depending on pH. So we'll discuss those later, but it's basically a little like a test strip or a solution that we add drops of to our unknown acid or base, and we get specific colors depending on the pH of that solution, of that acid or that base. And another reaction reacts with bases to form salt and water. What I'd like you to write down for this, and it's also the same with number 5 under bases, this is called a neutralization reaction. Okay, an acid plus a base produces salt and water. And this is something we will see later on in the notes again, but this is called a neutralization reaction. Now for the base, well, we start off with taste again. We have a bitter taste. So what's the difference between bitter and sour? Bitter, if you think of, well, it's not very good, but if I gave you coffee grinds and asked you to chew on those, that would be a very bitter taste. Dark chocolate, all right, if you go to the store and you buy dark chocolate where they start listing the percentages on the labels, I don't know if you've ever seen that, but there are types of chocolate that give you the percentage of how much cocoa is in there. The higher the percentage, the more chocolate, the more cocoa you have in there, and the less milk and sugar you have. So chocolate has that really nice sweet taste because of the milk and sugar that's added to it. But if you have a high percentage of cocoa in a chocolate bar, it is not going to be so sweet. It's definitely going to have more of that drier, bitter taste. Bases are also electrolytes. One specific type of reaction with a base is that they will react with fat molecules to produce soap. So this is how soap is made. Now they use different types of oils. You can actually have olive oil soap. You can have different glycerin types of soap, but the basic recipe to make fat would be to take a base, usually a naturally found base like lye, which is found in soil, and react it with fat molecules to produce soap. And glycerol is an alcohol, which basically can be washed away or burned off. Bases also change color with indicators. Bases are the other part of that neutralization reaction we talked about before. Now, something with bases that are unique from acids is their texture. And they have a slippery texture. And you know this if you think about soap. Okay, soap is obviously a slippery substance. So are egg whites, which are basic. So they have a slippery texture to them. Even if we were doing a lab and let's say we're working with something like sodium hydroxide, NaOH, that's a basic solution. And if you were to accidentally get some of that on your fingertips, as you washed it away, you would feel that slippery texture on your fingertips. If the same thing happened with an acid, let's say you accidentally spilt some hydrochloric acid on your hands, as you rinse that away, you wouldn't feel anything different. It just feels like water. But the bases definitely have a different texture to it. All right. And also, again, electrolytes. Most of the time we're talking about something dissolved in water that can conduct electricity. I also included salts. We are going to be talking about salt compounds quite a bit. Please add to your notes here that a salt is going to be an ionic compound. It is not just sodium chloride. I know we've talked about this in the past, but I just want to remind you, a salt does not just have to be sodium chloride that you put on your food. It can be any ionic compound. All right, so let's move on to the next page, which is going to talk about one of the two theories of what is an acid and a base. So we do have two theories. This one is a little bit more basic just because of what is in the formula. And then tomorrow we're going to start talking about another theory, which is called the Bronsted-Lowry theory, which has to do with the way the substance behaves with other substances. So the definition of an Arrhenius theory has to do with what ions are produced when the substance is dissolved in water. So for an Arrhenius acid, here's the part we want to highlight, the hydrogen ion. Okay, this is extremely important. When you put a substance into water and it dissolves, if hydrogen ions are the only positive ions present in the solution, that would be an Arrhenius acid, according to this theory. Now, if we jump down here to the Arrhenius base, instead of the H+, we're looking at the OH negative. Now for each of these, I have table K and table L listed. So if we take a look at table K, we have a list of common acids. And if you notice, most of them have H's as the positive ion or as the cation in that formula. So the HCl, the HNO2, HNO3, H2SO4, a majority of these molecules have that positive hydrogen ion. The acetic acid can be written one of two ways, but you can tell that you have that hydrogen ion again because it's right before that acetate -1 polyatomic ion, but you still have that H there. All right, so those are your common acids on table K. Table L, we have common bases. Now, this is a much shorter list than the acid list, but 3 out of 4 of these have the OH, have that hydroxide ion as the anion, as the negative ion. We have ammonia here, which we'll talk about tomorrow, but you can see that you have that hydroxide ion there. Now, with the base, there could also be other bases that are not on that list. And what you're going to look for is something with that OH, with that hydroxide. Okay, so right over there, you have the hydroxide ion. Normally what will happen is you'll have a metal bonded to that hydroxide, and that will make another type of Arrhenius base. So I believe I've seen questions in the past with magnesium hydroxide, lithium hydroxide, just other metals bonded to that OH. The diagrams at the bottom here show you how the compounds dissociate or dissolve into 2 separate ions. And in the acid, you have the HCl molecules go into water, and you have your H's, your H pluses, and your Cl negatives. For the base, you have your cation, which is your sodium here, and then you have your hydroxide. Another molecule that we are going to be talking about is hydronium. Hydronium is H3O with a +1 charge. Whenever we see hydronium, that is indicating that we are dealing with hydrogen ions because hydronium is formed when H bonds with water. This happens all the time. We're going to learn about how water is constantly dissociating and breaking apart into H and OH, how extra H's can bond to the H2O and make that hydronium. But whenever you see that hydronium molecule, that is referring to an excess in hydrogen ions. Okay, so when we start talking about pH and hydrogen concentration, that's when this is going to start popping up. But I wanted to mention that term now, so we start to kind of get used to hearing that. One thing that you want to be very careful of, when you're identifying a base, be very careful for alcohol molecules. They have OHs in them. Okay, that is typical for an alcohol, but they're not ionic. These are organic. Okay, they have nonmetals bonded to the hydroxide. So you have carbon and hydrogens bonded to the OH. That makes them an alcohol, not a base. So if you get a question that asks you to identify a base in a multiple choice question, I could almost guarantee that they're going to put something like this as the choices to try to throw you off. So you have to be very careful when you're trying to identify those bases. Anytime a question asks you to identify an acid or a base, you immediately go to table K and table L to see if they're there first. Okay, if you have the tables of those molecules, you might as well use that first. All right, so that is your lesson for today on the properties of acids and bases and the Arrhenius theory. All right, tomorrow we're going to jump into the Bronsted-Lowry and continue on and do a little bit of review with these first 3 pages of notes.